Hello everyone. So yeah, I changed slightly the title. So we'll talk today about variational bounds and variational inference, and I'll be trying to provide insights as to how we should do that. So this is a bit of a playful question because I'm not sure we'll have can you admit people in the?
Oh yeah, I'll do that.
Okay. I'm not sure, I think it's one of the biggest questions in variational inference. I'm not pretending that we'll have all the answers to that question by the end of the talk. So it's quite a thorough program, but basically we'll see where we get in that talk today. And I'll start by giving an introduction in which I'm going to give you the setting of this talk. So the setting is as follows. We're going to consider model joint distribution theta of x comma z, which is parameterized by theta, and x going to be an observation, and z is going to be a latent variable with its value rd. For this choice of model, my posterior density of the latent variable c, given the observation x, is given by this quantity. And you are aware of, we're interested in being able to compute from this posterior density. A key example where we need to have access to this posterior density, which is going to be of particular interest to us, is the case of trying to maximize the marginal log likelihood with respect to theta, which I define here using the notation L theta comma x. So this notation is going to be a lot, so good to keep it in mind. And it's just basically a log normalizing constant here, so the integral of my point with respect to things. So now why am I saying that this relates, like trying to perform maximum log likelihood relates to being able to sample the posterior density? But if you want to solve this maximization problem, you will need to be able to compute the gradient with respect to theta of this marginal log likelihood. Basically very simple calculations. So I've written them down here in case you don't trust me. But basically those calculations that will give you that this gradient with respect to theta can be written as the form written there. So basically it's the integral of my posterior density multiplied by the gradient with respect to theta of the log of my joint. So my posterior density does appear here, and I would really want to be able to sample this in order to get an unbiased estimator of my marginal log likelihood, like the gradient of my marginal log likelihood. And then that the unfortunate part of this is that for many important models, we're not able to sample actually from the posterior density. However, we do not despair because we're in like a masterclass about variational inference. So that we're going to be trying to maximize this marginal log likelihoods in using variational inference methods. More specifically, and this is the topic of this talk, we're going to be interested in variational bounds, that is to say, surrogate objective function to the marginal log likelihood that I will be able to optimize in a more tractable, let's say, manner, in an easier manner. So those variational bounds, again, as you've learned earlier during the masterclass, they will usually involve a variational family of probability density Q. And an example, which is the one that we're going to be considering in this short lecture, is to have a variational family of this form. So I will have Q phi. I will refer to that as my variational approximation. It will depend, of course, on Z, and I'll be like given X, where my parameter phi belongs to RL. Okay? So again, I'm working in R to the RL, RG, right, just to make it everything simple. So given those two information and given what you've seen so far, if I ask you to give me a variational bound, hopefully you're all screaming together, yay, the evidence lower bounds. And just to make sure that we all agree with the notation, I've recorded this definition here. So the evidence lower bound is going to be the integral of my variational approximation times the log of some weights, where those weights are written there. So I will use this notation throughout the talk, and those weights are my joint divided by my variational approximation. In our context, we'll be assuming that we can evaluate the joint, right? Because it's the normalizing constant, which is getting us into trouble, sort of. And since the variational family is something that we choose, we will also be able to evaluate Q phi and sample from there. This evidence lower bound can be written under the form here, right? Is the marginal log likelihood minus a Kullback-Leibler divergence, right? Which I call the exclusive Kullback-Leibler divergence. So I remember that, you know, we're not sure about what double bar means earlier. For me, double bar in this definition, I just wrote it down there so that there's no confusion. So here's the exclusive Kullback-Leibler that I'm considering. And as you probably remember, this exclusive Kullback-Leibler is an object that is non-negative. So I have this inequality, which tells me that the evidence lower bound is indeed a lower bound on the marginal log likelihood. So if I want now to try to perform maximization of the marginal log likelihood, this tells me that this object is probably going to be an interesting one to try to optimize over, right? By maximizing this one, I'm probably going to increase this one. So at this stage, yeah.
One question: what does exclusive mean here?
I wasn't there at the first part of the workshop, but you know that you've got like different behavior for the Kullback-Leibler divergence. So you might have heard it under the name forward or reverse. Oh, yeah. So it's the same, it's exclusive and inclusive. So exclusive is the one where here, imagine I sample from Q phi, right? And P is 0. This blows up, this is infinity. Okay, so this is what I meant by exclusive. This will exclude, like, you won't be able to have Q phi that has a support that is bigger than the one of the posterior density. So it excludes those areas. Okay. Thanks for the question.
Thank you.
It's an important one, especially when we play with variational bounds and divergences. All right. So at this stage, I just want to make a slight remark where here you might have noticed that I've told you I'm going to do marginal log likelihood optimization. I believe it's a bit different from what you guys have seen so far, in the sense that in traditional variational inference, theta was sort of constant until then, right? You were not particularly trying to maximize the marginal log likelihood, but you were to approximate the posterior density. And in that case, minimizing the exclusive Kullback-Leibler divergence was strictly equivalent to maximizing the evidence lower bound. Here, we're considering a slightly more general framework because I'm going to be wanting to do optimization with respect to both theta and phi. This is closer to the variational autoencoder framework, which will be introduced in depth in the afternoon lecture. And basically, in the context of this talk, what you need to do is that I'm not just optimizing with respect to phi, I also have an optimization with respect to theta that will be happening. And if you look at this expression, you will see that if you optimize just with respect to phi, then it's kind of the same as traditional variational inference. I'm trying to minimize this term. So if I optimize with respect to theta, so I'm going to be trying to maximize this term, and I will have here what I will call a regularization term. Is that sort of clear for everybody? Okay, so...
Sorry, I missed it. Can you repeat the last sentence?
So if you optimize with respect to phi, this objective, since this does not depend on phi, you will be trying to minimize Kullback-Leibler. So this is close to what you've seen so far in variational inference. However, I'm adding on top of that a maximization procedure with respect to theta. This, you can interpret it as trying to maximize your marginal log term minus this term, which is a regularization term, which will ensure sort of that your P of theta does not stray too far from your approximation. Is that clearer that way? Yes. Okay, so we've got all of this, and now we want to design a procedure to train our evidence lower bounds so that, you know, we optimize our parameters theta and phi. And here I'm going to be relying on yesterday's morning talk to give you a procedure on how to train the elbow. So this hopefully should, remind you of what happened previously. And basically for me, training with an objective function is going to be about like 4 main steps. The first step is to ensure that I can track my objective function. Okay, so I've got the evidence lower bounds, but in the general case, this quantity is intractable. So the first comment I want to make is that I can track my evidence lower bounds by just resorting to usual Monte Carlo sampling and this estimator where, I've got Z1 up to Zn that are sampled in an IID manner. Okay, good news. I can track my objective function. So, see what happens as I change theta and phi. The second thing I'm going to use is the parametrization trick. This rings a bell for everybody, right? Yes, you've seen it already. And so here I'm just going to give you the notation for this talk. And this parametrization trick is going to tell me that Z can be written under this form. So it's going to be F of epsilon phi, and I'll keep a dependency in X. And what this reparametrization trick does, just to refresh your mind, is that if I sample epsilon according to Q, then I will have that Z is distributed according to Q phi. This reparametrization trick is about separating the source of randomness in epsilon from the parameter I'm trying to optimize over phi, which has been shown to have good properties when you're looking at the gradient, right? It's not always true. You've probably heard about this paper by Shakir, Mohammed, and co-authors, where they're also looking into control variates, but it's still the standard. Reparametrizing in this context still quite the standard, even though we can try to find alternative ways.
Can I just ask, how can this ever be like difficult to do?
Reparametrize?
Yeah.
Yes.
Okay.
Yeah, it's not always the case. Usually in the context of variational autoencoders, you have like a normal distribution that you can easily reparametrize. Yeah, it's not a given that always works, which is why people are interested in like, oh, does it actually always perform better? How do I do when I cannot reparametrize? And how can we develop better control variates methods so that we control our gradients and their variance? Yes, good point. All right, so that's my second step. The third step is actually to compute the parameterized gradients of my evidence lower bounds. So here again, I'm building on what you've previously seen. So if you just apply the Lotus, I think that's the name, Lotus rule, you get that the gradient with respect to theta and phi of the evidence lower bound is under this form. Is it bothering anybody, or is everybody agreeing with this expression? I'm waiting for a yes.
Yes.
Fantastic. Or for a potential no. So here's my expression, and basically my last step then is to say I'm going to be actually able to perform stochastic gradient descent with respect to both theta and phi by deriving an unbiased estimator of my evidence lower bound. So I'll just have to sample according to Q, epsilon I, epsilon 1 up to epsilon n in an IID manner, and here's my objective function. So this is very nice because then I'll have some sort of theoretical guarantees of the entire procedure. So this is kind of the reminder I wanted to give you guys with the notation before we kind of move to the let's say the core of the talk. And basically, I think a question which might be a bit naive when we look at this expression that I showed you before is, okay, interesting that we've got this Kullback-Leibler divergence term, this exclusive Kullback-Leibler divergence term here. And the naive question is that, can we change it? Because if you're a bit familiar with optimization, you do know that the choice of the regularization matters. So you can ask a similar question in the context of variational inference. And basically, now I'm going to introduce to you to one case where we're going to change this regularization parameter. And I guess the underlying question is that, yeah, can we change it, and will it make our life better somehow? And this brings us to the VR bound. Everything's clear so far? Good. So the VR bound is an object that has been introduced in Urich's paper by Leon Turner in 2016, and it's an object that is defined for all alpha that is non-zero and alpha that is non-1 by the expression that is here. So again, you will have the weights that I was showing you before. I've wrote them twice to be sure that you don't remember what they stand for. So it's the joint divided by my variational approximation. And this VR bound is going to be given by this expression. So I've got 1 divided by 1 minus alpha. We understand why alpha, we don't really want it to be 1, times the log of the integral with respect to Q phi, my variational approximation, once again, times the weights up to put to an exponent 1 minus alpha, and all this is integrated with respect to z. If we write this into, trying to fit with the expression that I was giving you before, this is going to be the marginal log likelihood minus this quantity, which is called Rény's alpha divergence. So here's the choice of the divergence. Like now we're seeing another one appear, which is not the traditional exclusive Kullback-Leibler one. This Rény's divergence, Rény's alpha divergence is also defined for alpha as non-zero, non-negative and different from 1 by this expression. And if you kind of want to compare the two, it's pretty much like what happens with the evidence lower bound in the exclusive Kullback-Leibler. So these two expressions resemble one another very much. The sign here changes. And here I'm working with the posterior density instead of the joint. Okay, so it's the same thinking process as what we've done with the exclusive Kullback-Leibler and the evidence lower bound. All right, good. Fantastic. So now we want to get like an idea of, like we've got an extra hyperparameter and we want to know how it plays a role, what happens to it. And, maybe we'll start by trying to solve the fact that it's supposed to be not 1. So as it turns out, if you let alpha go to 1 in this Rény's alpha divergence, you recover the exclusive Kullback-Leibler, which gives us the sense that, this Rény's alpha divergence, in fact, is just an extension of what we've seen with the evidence lower bound. So I've written the proof there, should you be interested, or because I was like, maybe they're not going to trust me just yet at the start of the talk. And basically, just to see how it works is fairly simple. So, just bear with me a little. I'm going to introduce this function f alpha, which corresponds exactly to the term that is here. And I'm going to notice that if alpha is 1, so if I put a 1 here, this is equal to 1, okay? And then I'm going to differentiate my f alpha. So it's like, I'm just going to assume that, I can differentiate at once. So basically, if I differentiate, here, I'm going to have to take the gradient with respect to alpha of this quantity. And this is like exponential alpha minus 1 log of this, which gives me this expression for the derivative of f alpha. Okay, hopefully good for everyone. And if I now look at my limits when alpha goes to 1 of my Rény's alpha divergence, and I use the definition of f alpha and the fact that f of 1 is equal to 1, I have that this is the limit when alpha goes to 1 of log of f alpha minus 0, log of f1, divided by alpha minus 1. And we're all like experts at, differentiating. And we know that basically this is you just need to differentiate this function and to evaluate it at 1 to get the result. So its limit is f prime of 1 divided by f. Good for everyone? Yeah, this is 1. And this, you just have to plug it in there. So this terms cancel. And this is my exclusive Kullback-Leibler divergence. Okay, so this holds. Second thing that holds is the fact that because this is a divergence, this is also non-negative, like the exclusive Kullback-Leibler divergence. So my variational Rény's bound is going to be a lower bound on the marginal log likelihood. And one thing that also you might notice is that if you take alpha equals 0 in there, which you can do, you will recover the marginal log likelihood. The takeaway message, the high-level message, is that the VR bound is going to be a generalization of the evidence lower bound, which enables us to interpolate between our marginal log likelihood and the evidence lower bound. Okay. So this is all nice, and then you'll be like, yeah, it's nice that you've got this alpha parameters and that you recover.
Can you go back 1 second? Thank you.
What like?
No,
what did you want to see again?
It was an equality or smaller than equal, but it is an equality.
When
We have 0.
it's 0, yeah, because this is 1 this term. So it's just, yeah, Q phi times Q phi times P theta, times your joint. So integral of your joint, and this term is 1.
Are they strictly increasing as alpha goes?
Yeah, I think they've got like a monotonicity thing. Yeah. So I'm not sure it's increasing or decreasing. I'm like,
Okay.
but yeah, that's definitely, the monotonicity. Yeah.
Yeah. So basically, when alpha is between 0 and 1, it interpolates between
Yeah.
When alpha is between 0 and 1, it interpolates between the log likelihood, the elbow.
Yes.
And if you consider like alpha larger than 1,
Yeah, it's an upper bound. Like it goes. It's the thing that you were saying. It's like increased. It's a lower bound, and then it's just the limit. I think it's written in the paper that I'm mentioning here, which is Leon Turner and Europe's 2016. So they look into all the edge cases. In my case, I'm mostly interested in alpha bigger than 0 and like between 0 and 1, but I think it's written. I don't exactly remember, and I don't want to say something wrong. But just have a look. Thanks for like querying me on Ren's business. I mean, that's definitely the topic of today. I should know my divergences better. Okay, so I was saying that's the high level message. And now we might be interested in seeing whether, changing the regularization is important or not in practice, right? So this is the question I've written there. How does this regularization term behave? And I'm going to take like a super simple example, in which I'm going to be looking at my Renyi's alpha divergence between a certain Q and a certain P. And I'm going to be trying to find the Q that minimizes this alpha divergence. So let's say traditional variational inference task. And P here is going to be a normal distribution in 0 and with covariance matrix of this form. So basically it's 3 on the diagonal and then -2 on the rest. This is dimension 2. So I've got some form of correlation happening. And for my Q, I'm going to assume that it's a mean field. So you guys are experts at mean field, so I don't really need to explain this to you, but I will have 2 mean parameters and 2 standard deviation parameters here. And I'm just going to be trying to find those who match the best with my target here. So my target is in blue. And I'm going to try to see which one is the best as a function of alpha. And I have several approximations for various values of alpha. So alpha equals 1 is the red one. And as I decrease, I go 0.75, 0.5, and 0.25. So what basically I'm trying to tell you there is that this choice of alpha will have an impact on the optimal Q that is going to be returned, right? So if I'm optimizing with respect to phi sort of, this choice of alpha might play a role in how well, it might approximate. So this is not definitely an approximation, but we see that in terms of support. If I change alpha, I get better support, which might be important in practice, right? Because I might get a better approximation if I change the value of alpha. Okay. Good. So now that I've hopefully told you that this is important to try to change this regularization term, how does training happen? We've seen how training happens with the evidence lower bound. I've told you it's 4 steps. Let's see how those 4 steps transfer to the VR bound according to Leon Turner. Do you see this? Yeah, you see this actually. Let me hide it.
No, the one below. The one below.
Thank you very much. Yeah, a bit better. So first thing is what I was telling you before. I'm going to be trying to see if I can check my my estimator, if I can track my variational bound. So basically what they do in this paper is that they use the estimator that is given here. So they just approximate the integral here using typical Monte Carlo sampling. So I've got ZY according, distributed according to Q phi, and I've got like n of them in an IID manner. Second step is going to be the same. Still going to be assuming that we can do trick. And third step is to derive the gradient of the VR bound in the reparameterized case. So here's the moment where if you want to shine, you can go to the blackboard and you can try to write down this reparameterized gradient. The applying weight. Is anyone tempted to do it? like, for example, ND.
No, this is Peter.
Like just saying this out there. All right, so it's a very simple like calculation, and I'm just want to write it down. It's also written down here, so depends which one you want to follow. But basically, just want to have the gradient with respect to theta and phi of my variational rebound. So I'm going to probably drop all those parameters, Okay, so I'm going to say this is the 1 minus alpha. Don't really care. And so I've got gradient here of log of something, of an integral. They're all experts. Oops. So this is going to be times z integral, right? Gradient theta and phi of integral. Now I've assumed that I can reparameterize. Okay, so I'm just going to be writing down actually what is going on here. Can everyone see, by the way, the quantity that I have with the lotus rule? Okay, this is the reparameterized integral, and then I just want to have the gradient of this quantity, basically. Everyone follows? Lotus rule, if I take the gradient and I'm under, the pure differentiation assumption, I can go through the integral and I can bypass this term. So I'm like u epsilon of w phi f epsilon. Think this one through. Okay. So again, continue. Integral there stays the same. Actually, let me. Are you not allowed any mistakes? Okay, so I need to differentiate this term. There's the 1 minus alpha that's going to appear, which is going to simplify. I'm just going to remove it. Then there's w to the power minus alpha. Yeah, so I'm writing this here. I don't know if it's readable because I'm standing in front of the blackboard, which is not as smartest idea.
Where's the camera?
No, it's there. No, it's there.
Oh yeah, good.
W, of course. And this is the same integral as before. Everyone agrees with that? It's badly written. So I've just differentiated this term, the 1 minus alpha simplified. Then I've got this term to the power minus alpha and the gradient of the W. And so I'm almost done. I'm just going to use that for my weights. This is equal to weights. Sorry, being lazy here. Cool. Right. So the gradient of respect to theta and 5, the weights is the weights times the gradient of the log of the weights. Right. Right. Andy, you look very perplexed.
That's good.
It's a good thing you weren't there, right? You're enjoying your life. Basically, if I just replace now and there, I'm going to get the desired expression. Oh, sorry. Oh. Actually, there's nothing there left, which is integral epsilon here. My weights. I'll actually try to write this one in a readable manner because it's the one that matters.
And the one over,
Sorry?
and 1/1 minus alpha, is it?
It's simplified when you differentiate it here.
Oh, yeah, okay.
So this is the expression that we get, which hopefully everybody agrees with. I left the room because it was too easy. Okay, so this is the expression we have, and this is like common of, trying to, when you're parameterize stuff, those are the typical tools that you use. Okay, and this is just what is written there. So hopefully the two formula agree. They are. So, okay, and last step, which is the fourth step, is to give an estimation of this integral, of this gradient of the variational really bound with respect to theta and phi, which they give under this form. Okay, let's do. Whoops, yeah.
Sorry, can I ask a probably silly question very quickly?
Yeah.
From online. When you sample from these, is it not biased then?
It's far from a silly question. It's like, it's going to help us transition to the next slide. So I'm just going to ask you to be slightly more patient, and I'll address the point you're making very shortly.
Thank you.
So this is the whole training procedure. And the first thing I want to comment on is I proved in front of you guys that if I take the limits when alpha goes to 1 in the variational really bound, I recover the evidence lower bound. So a sanity check is just to ensure that if I, take 1, like in the definition of my gradients, I recover the 1 of the evidence lower bound. So it is actually true, and you can see it here. If you just put 1, this term is 1, this one is n, so you've got 1/n sum of gradients of the log weights, which is what you had in the evidence lower bound case. So it's just a sanity check to show that what is actually extension of the work done, what usually is being done in the evidence lower bound case. The second comment I want to make is that people have observed that actually working with alpha that is not 1, and in particular alpha that is less than 1, yields positive empirical results. So it's, kind of confirms what we're saying, as in it's important to play with this regularization term. However, and now I think it was Daniel, we go back to, the problems that might arise when we work with this variational really bound. So the first one is that the VR bound can only be estimated using biased Monte Carlo estimators due to this log function. So this could be like one problem, but it's actually not the worst, because you're like, okay, it's just a biased estimator, but maybe if I take n large enough, it's not too bad. Then there's a second problem, which I think is a bit more worrying, which is in, the approximation that is given here of the variational, of the gradient of the variational really bound. Because this is the ratio of two integrals, this is also biased, meaning that unlike the case of the evidence lower bound, where you were doing like unbiased stochastic gradient descent, here you're working with biased estimators. So in terms of theoretical guarantees, this is not great at all. It tells us that, we don't have the basics, as in, if I do my Robbins-Monroe or, traditional stochastic gradient schemes, I don't really know what's going on. All right, so we're still optimistic that there's like positive empirical results, so there's something to uncover here.
Sorry, could you go back to the slide where you had the concentric normals, just to see what alpha smaller than 1 does to the support?
Alpha smaller than 1?
Also, the lower alpha goes from 1, then the bigger.
Yes, yes, which you kind of understand, I guess, with this term. You lower the value alpha, so you get, I think, closer to the marginal log likelihoods. So it becomes sort of it's important if the support do not match that much.
Mm-hmm.
Yes.
Okay.
Makes sense. Any other questions so far? Or can I continue? Yeah. So, okay, I said there's 2 problems. Lee and Turner were aware of those problems, right? They didn't just dismiss it in their paper. Oh, it's biased, it's fine. And in particular, they said something about the first problem, which I'm going to try to be summarizing in a few words. So they were like, okay, we need to look into the properties of the biased approximation of the VR bound. And they did this by looking into the expectation of the biased Monte Carlo approximation, which is the quantity I'm introducing here. So I had like Z1 up to Zn. So when I take the expectation, I'm going to integrate with respect to the products from I equals 1 to n of q phi of Zi, knowing x. Okay? So they were like, okay, we don't really know what goes on with this approximation, but let's look at what happened in expectation. And they proved two things, which I think are super interesting. The first one is that if you take alpha that is less than 1, and n is an integer, you can show that by taking n equals 1 here, you recover the evidence lower bounds. And in fact, the expectation of the biased Monte Carlo approximation is going to have a monotonic property as a function of n. And as you increase n, you will get closer to your initial, oh, damn, this should be VR. I'm sorry, this was previous notation. This is the VR bound. Sorry, guys. Yeah, wrong notation. How unfortunate. Okay, so this is VR. I was like, poor them. They just saw this L out of nowhere. Basically, as you increase n, you will get closer to the VR bound, all right? In a monotonic manner, if you look at the expectation, which is kind of reassuring. This tells you, okay, if I do play with my n.
N increases, you said.
Yes. Here, like this n, and this is n plus 1, and this is n equals 1. Okay, so you've got monotonic behavior. You've got this idea that, okay, if I increase my n, I'm going to get closer to what actually was my initial targets. And in fact, they also proved that if you let n go to infinity, you actually recover the VR bound. Yeah, I'm sorry for this L. Terrible.
No problem at all.
No, I'm like devastated. Okay, so that's what they said about problem 1, and they didn't address too much problem 2, but we'll look into that later. And for now, just want to like summarize everything that we've done so far. So I have like several slides that are called like at this stage, and this is basically the moment where if you want to take a break and ask a question, you can definitely go for it. So what have we seen thus far? We've seen that the VR bound seems to be an interesting generalization of the evidence lower bounds. We've looked at an approximation of it and an approximation of its gradient, and we've identified two problems. The first one being that the approximation of the VR bound is biased, and the second one is that the stochastic gradient descent of this VR bound is also biased. We've seen that there's a way to sort of alleviate the first problem, but we haven't seen anything yet about the second one, which for me is the worst one. All right, so that was the state of the art, and we arrived with my co-authors, and we said this quantity is actually super interesting. How about we try to see this expectation from another angle? How about we try to think of this expectation as a variational bound? And from what I'm going to say from no one is about this new paper that we've put on archive with my co-authors, so Joe Benton, Yu Yongshi, and Arnaud Doucet, which we've called like alpha divergence variational inference meets importance weighted autoencoders, methodology, and asymptotics. All right, so I'm going to get now a bit into the deep end, and I hope that you'll follow me there down the rabbit hole. Any questions so far? Badr is smiling very happily. Good. All right. If there's no question, then we can move on to this bound, which we're going to name the VR-EY bound. Hopefully the name will become more obvious as we progress. All right, so I'm going to restrict myself to alpha that is between 0 and 1. This is the range I'm interested in. I'm going to exclude 1. And I'm going to introduce this formally as the VR-EY bound. If I work in that range for values of alpha, I will obtain that the VR-EY bound is a lower bound, which can be estimated using estimators. So hopefully Daniel is starting to feel a bit better about the quantities we're working with. And even better, if I take the gradient with respect to theta and phi of this new VR-EY bound, here's what I get. So Andy, how do you feel about deriving this one? Do you want to? No, I'm teasing. So basically using the same Lotus rule as before, Here I'm going to replace all those Q phi of Zi by Q of epsilon I, and the log of my sum here, renormalized, of my weights to F, because Z is going to be expressed as F of epsilon I, phi, and X to the power 1 minus alpha. And basically, simple derivations give you that this is the gradient of this VIY bound. And the key point here is that this can actually be approximated in an unbiased manner. And in fact, the estimator that we get is the one we had previously using the VIA bound. This has very strong implications in the sense that what we get is that this VIY bound is providing us with theoretical guarantees for the previous stochastic gradient schemes that were used in variational inference methodology. So this is important to make sure that it's like crystal clear for you guys. We've recovered this estimator, right, in the stochastic gradient descent using an unbiased procedure. And we've recovered the estimator of the VIA bound in an unbiased manner as well. Okay, so in a sense, we've made all these methods more theoretically sound, because now the stochastic gradient descent, we fall back to what we know, unbiased stochastic gradient descent, Robbins, Monroe, and what already exists in the literature. All right.
Can we go over this one more time? So that could be used as a bound,
Yes.
and then we can approximate the bound that way.
So the bound, this one?
Sorry, that can be used as a bound, and then if we take the gradient of that,
Yes.
okay, and then that's the expression, we can approximate it that way.
Yes.
And
This is unbiased, because I'm sampling according to Q.
Mhm.
Yes, and IAD manner, epsilon 1 to epsilon n, right? This is just an integral with respect to this product, so just need to simulate every one of them.
And you said it's important because it also comes out from again.
Because
Because it's the same as something else?
This stochastic, estimator was the one we saw previously when we were doing the EIA bound. If you look at this one, okay, then I'm going to move forward a bit. So basically,
Same,
sum
yeah.
weights power 1 minus alpha divided by the sum of the weights 1 minus alpha to the power minus alpha gradient of the log weights. Okay, I move forward a little bit and I get the same estimator. So we
Okay.
recovered this estimator, which was used. That's what they were using in their paper, and that's what practitioners have been using. We recover it, but we show that it can be seen if you use a different objective function, if you use a different bound, it can be seen as an unbiased estimator of the gradient of this bound.
Okay.
If that makes sense?
In the previous context, it was biased, but now we get the same thing, but isn't biased of
Yes.
something else.
Change the objective function. So it shows that maybe what they were doing by working with this VR bound was not actually the best bound they could use for like theoretical purposes. You have the same. Now everything makes more sense. The quantity that we use to track the convergence makes more sense, and the gradient descent also makes more sense.
So Kamélia, just to understand, so basically you're referring to this as a multi-sample bound.
Can we come again?
Don't they call this multi-sample bounds sometimes as well?
Yeah,
Yeah, okay.
fantastic. Oh, I love you people. You're asking all the good questions. Let's look at particular cases.
Can I ask one question? Is the fact that this thing is also a lower bound, is that just a simple consequence of the previous stuff, or you have,
Simple consequence.
is it a consequence of the stuff you've already said, or do you
Good
have
order,
to stuff?
sense inequality, and the fact that it's a lower bound. No, it's a good order, sense inequality. So basically, you can always between 0 and 1. You can bound this by the VIA bound. Okay, and the VIA bound, it's a lower bound in that range. So it's like not too just.
There's nothing, okay.
Yeah, I mean, you're using that the VIA bound is a lower bound to the log likelihood, but you're just adding, basically, if you want to do it yourself, just try to find the VIA bound from this one. Shouldn't be too hard, like just a Jensen, I reckon. So you put this term inside there, and this should be your variational radius bound. Okay. Special cases. First special case that we want to look into is the case alpha goes to 1, because we want to check that, we are still linked to the evidence lower bound. So I'm not going to do the proof, You'll have to trust me, or I have to send Andy to look like this. But basically, if you let alpha go to 1 in this context, you will evidently get. Now, another case that I haven't mentioned just yet, but is super important, is the case alpha equals 0. So I don't know if you're familiar, maybe, if I write things under this form, does it speak to you? Yeah? Fantastic. So this bound is actually well known in the literature, and it's called the importance weighted autoencoder bound EY, which is why we gave this name VREY bound, and which is why we're like in the title of the paper, we're like, oh, variational inference methods with the alpha divergence are actually meeting importance weighted autoencoder. Because when you put alpha equals 0, you do recover this bound. Okay, so this bound, just a bit of background knowledge, but not too much to be honest, is an extension of the evidence lower bound. If you take n equals 1 in there, this is the evidence lower bound, which was shown to lead to positive empirical results. So what we're doing here is that we're connecting different literatures while having the same goal in mind, trying to improve over the evidence lower bound. Okay. Compared to before, where we had that the VR bound was interpolated with the marginal log likelihood and the evidence lower bound, we're now in a case where we interpolate between the EY bound and the evidence lower bound. And the second line is kind of a summary of what I've said thus far, which is that this EY bound, which existed in the literature, has now been extended in a very theoretically sound manner to the BR bound methodology, sort of, if you know, putting a lot of and phrasing might not be the best, but if that's what we wanted to achieve, like to interpolate between the EY bound and the elbow in a sound manner using those alphas, this was the way to do it. Okay. All right, so summary, the VREY bound gives us theoretical guarantees behind various existing schemes, and it is the natural, theoretically sound extension of the EY bound that comes from this kind of literature. Any questions?
So I just wonder whether in the literature there are results on stochastic gradient descent biased.
Yeah, they haven't been applied to this specific context. While if you're unbiased, then it's very easy to have those guarantees. You could go biased. The biased way, it hasn't been done in that case. Should this is in fact not necessary in that context. So if you have no questions, I have one, which is like, now that we have this VREY bound, are we able to sort of understand a little bit better its behavior as a function of alpha? Because I've been telling you, yeah, alpha seems to play a role. Can we get some insights about it? And I suggest we take a short break, because it's like 55, just to, I think it's a good point to break. And we come back, let's say in five minutes. How does that sound? Sounds good? Okay. And if you've got any questions in the meantime, you know, please feel free to ask them.
Did you find any paper?
Yeah. One is
Bit of confidence for next month.
That's why I like to have it like, hey, I love you.
Walk into a drinking game. Every time she says alpha in 01.
there's really
Super cool stuff there.
is
Yeah, and so I have actually
Gibbs sampling very good.
but I want to just
Very high. So very nice.
Okay.
but what
So
Yeah, you've already sent the slides to Francesca, right, so she can share.
and uniform except
but I
actually also to me that's
Oh, criminal.
you do it.
Yeah, we want a refund, pleplease. I want my money back. It's happening.
different out.
because I thought it's better.
It's a bit interesting.
People that
I can't
just like
completely tell whether it's practical, but it's something like
For me, everything.
And another question is that so the original elbow have like which log likelihood minus the
Actually
scale.
have to be in three.
We,
And when you change that,
It has to be the largest
part is that
en fait, quand tu
less.
sais que c'était une KL,
Okay.
une exclusive KL,
Yeah, so it's, yes.
approximation.
Then you start filling out with cubes that have half the side
Plus
length,
de flexibilité. J'ai pas regardé, mais oui.
same property,
Okay,
Ensuite,
and then you go play it down, and
okay.
so this is like decomposition, which I think
je
Veronica
pourrais
can help.
peut-être réussir à remettre à la sur l'effet approximation.
Oh, no, it does, yeah,
Okay.
but it kind of doesn't matter.
Parce que je me laisse.
So if you say you had like
Ah,
oracle,
alors,
this.
Something is that, so then it will, what are they doing? So something is.
So I think conceptually, so I don't think this is exactly what they're doing, but conceptually, it's a random walk on which cube you live in.
Yeah, I'm definitely not.
On,
On cubes inside the set.
okay, okay.
And then you're
What do you need, bundle or?
no, because so you know the construction I said you have to be far away from the boundary.
20 slides is like.
So you will eventually
It's a
get
new
there.
personal record.
But you.
I'm so happy that you're
Theorem, which is like,
I help.
but
Those-
you continue this.
It's a lot. Experience, I think.
Yeah.
With environmental.
Be more.
Less and less time.
Let's go.
Smaller.
That would
I
be
think it
top.
would be so enjoyable. I don't know if you would enjoy that as much as we would.
Going to the ball.
Yeah, so like if Andy goes, it would take
Andy's like,
long.
and his face is like, no.
Second time, if you'd have poked at him, he wouldn't have done.
Pays.
Try to read it off the board when it's like faded out, just. Really hard.
To be fair.
So they really
I'm like, come on, Andy's
think
written.
reason is
And he was like, nope, I walked 45 minutes this morning.
So-
That's
Ib sample
that's
to the cube.
Wow, that's just.
Just me.
And
Our bus.
in the context of this sampling, it's known that the hard code is.
minute then. It matters.
Yeah.
Okay.
I know.
It's like
So
automatically now, she didn't like.
have the sort of very coarse grid that so you non-adaptively.
Oh, yeah, I know.
Used to walk there,
Not well-
quick way spell.
Yeah, but dude, it's so much time.
Yeah,
That's.
I think stepping outside this
They, and just use the chair.
decomposition, you're always on the inside, it's always cube. Actually, you have if there's two cubes that share a face with one another. Yeah, and there's not,
We still have 50 slides to go.
like, side will be within a factor of,
So get those slides.
don't even have heterogeneous.
Okay.
So I think I'm trying to work out what the algorithm is, because they're a bit coy about it. So I
Actually,
think they can define an algorithm set of cubes, but maybe it corresponds to a Gibbs sample.
Okay, I think we are about to start, guys.
Okay.
I think we're about to start.
Yeah, I think this.
so this very nice break. We need to go back to our, which was, can we understand better the behavior of the DIY bound as a function of alpha, which is between 0 and 1? We know it's the evidence bound. And especially can we get a sense of, what this n is actually. So that's the part 4, where we're going to study the VIY bound. So it's quite a long part, and I'm going to split it up. First, I'll describe to you what is going to be the quantity of interest in this section, which I will refer to as the variational gap. So the variational gap is my VREY bound minus my target, which is my log likelihood. So this is something that is always non-positive. And I want to get a sense of how this behaves, like what happens if I increase n, am I actually getting closer to my marginal log likelihood? Yeah.
You say always positive,
No.
always non-positive.
Yes, because it's a lower bound, this term, on the log likelihood, marginal log likelihood. Yeah, so always non-positive. Yes. All right, so it seems like a good idea to look into this one. Because it's going to give us a sense of what happens as I play with n, and if whether or not I get closer to my marginal log likelihood. And this can be rewritten as the interval there, which I've just written down to show you that it involves those weights. So those are the weights from before, but now I'm adding like a bar on top of them. And I'm going to refer to them as the relative weights. So those are my previous weights divided by the expectations. So I'm just doing this so that the expectations with weights are 1. So it's like something a bit like minor, but in fact, those relative weights are the ones that are going to appear in the rest of the talk. So just think of them as the normalized versions of, so that they have expectation 1. And if you want to write down exactly what they are, they correspond to the posterior density divided by the variational approximation. So kind of something that you would want to get as close as possible to 1. Okay. Good. Yeah, just a little bit, a slight remark. I'm going to drop the dependency in X in the rest of the talk because I think we've seen it enough and it's awesome. And now we can move into how we in fact study this variational gap for the values of alpha indicated here. So I'm going to consider in this first part the case where n goes to infinity and d is fixed. Okay. Why do I consider this case? Well, it's because I know that very cool people at Europe's 2017, Madison and co-authors, I think Arno is a co-author of that paper, and then Domke and Sheldon in the following Europe's conference looked into the variational gap in a very specific case. So this kind of follows what you were saying, as in people, they know about the EY bound, it's a common bound, and they've tried to study it. So so those two results are, in fact, so they follow one another, and I'm going to talk about Domke and Sheldon because it's a refinement of what they found in Madison and Schultz. And informally, what they have shown is that the variational gap in the context of the EY bound, so when alpha equals 0, can be written as this under this expression. So you've got minus gamma 0 squared divided by 2n plus a term that is negligible in front of hello. Short-lived interest is which is negligible before 1/n. And here we need to say what gamma 0 squared is. It's the variance of the relative weights. That's kind of why I was introducing them, because they're going to appear in the rest of the talk. All right, so let's try to make a few comments on this result, which like the first one's going to be ready. Key insight of this paper. This first comment is that playing with n is actually very beneficial to reduce the variational gap, right? Because I've got a decrease that's in 1/n, so I've got a fast rate, and this will go to 0 very quickly as I increase n. So it means that, you know, it's actually a pretty good idea to work with this, to move from the evidence look at this EY bound. So this is nice, and you're like, okay, can we sort of reuse their proof for our purposes, namely to deduce the results about the variational gap when alpha is in a wider range. So, you know, alpha that is between 0 and 1 excluded. Turns out that we can. And here's the result that we get. I'm just going to give you like kind of an overview. So alpha is in that range. Then I'm going to introduce some quantities, this one, and this gamma alpha squared, which is a variance term.
With alpha 0,
Yes.
things reduce to what? To the VR. No, wait.
So VR EY is alpha equals 0. This is the EY bound.
Yeah, exactly. That's what I meant. Okay, good.
Okay, yeah.
Be sure of that.
Very good. That's, you know, this is an important part.
Could that L also be the VR?
Yes. Oh no. Did you really have to point it out? You know, adding salt to my wounds. So this, this is in fact this is a VR and not an L. Those are the notations of the paper, hence the mistake. And I've got this gamma alpha squared, which is going to be variance term involving those weights, basically. So then under some conditions, which I will come back to in a minute, I can write my variational gap as this expression. Okay, let's unpack this expression together. there are two terms. There's this term, which is minus gamma alpha squared divided by 2n, which resembles a lot the one that we saw before, and which is going to decrease at a fast 1/n rate, and which will depend on this gamma alpha squared. And then I've got an error term here, which will decrease away from 0 as alpha increases, right? Which is not great. So we're getting further away as alpha increases. Basically, the high-level message of this theorem is that this hyperparameter alpha that we've introduced is going to balance between two terms. One term that is an error term and one term that goes to 0 as I increase n. Okay, so this kind of gives us insight as to why people got those good results by playing with the value of alpha. And now I want to go to this some conditions that I've written there. Basically, there's a few things that you need to know about these conditions. That's why I didn't write them down. The first one is that, do they relate to the conditions that were in Domke and Sheldon? And the second one is that, how do they evolve as a function of alpha? So those conditions, they exactly generalize the conditions from the paper by Domke and Sheldon. Right? So if you take alpha equals 0 in our conditions, the EYA, then those are exactly the conditions in Domke and Sheldon, and they do not get more restrictive as alpha increases. Okay, so this kind of tells you that you don't really lose anything by increasing alpha because your conditions, they're not getting stronger. And in fact, we've proved this result, but what we think is that if you increase alpha in practice, your conditions are easier to satisfy. So we haven't proved it, but that's what we think. And one last comment maybe is that this gamma alpha squared that appears here is controlled by our conditions, because you could wonder, okay, what's this variance term? Well, our conditions are so that this term is controlled. All right.
Silly question. I'm stuck on point 2.
Yes.
An error term VR minus L decreases away from 0 as alpha increases.
So I'm going to ask you a question in return.
Okay.
What happens if you take alpha equals 0 in that error term? This is the VR bound.
It's just the elbow.
Is that what it converges to? I don't remember what it converges to.
What is the VR
Zero.
bound when alpha is 0?
Remember. What is it?
When alpha is 0, that thing is 0.
Alpha is 0. The VR bound is the marginal log likelihood. It
Okay.
was one of your questions. That's why I threw it back at you.
Okay.
Without any sense of force.
That'll teach you for asking.
Basically, this term is going to be the marginal log likelihood minus the marginal log likelihood.
Okay.
So this is 0.
When alpha is 0.
Yes.
When alpha increases,
Yes. This goes away, so this becomes more negative.
okay, that's right.
And
Gotcha.
alpha equals 1, is that the elbow?
Yes.
Okay. Gotcha. Thank you.
Fantastic. All right. So yeah, so this is just because we had a happy moment when we saw this result, because to the best of our knowledge, it's the first result that kind of sheds light on how alpha might play a role in the VIY bounds. People didn't have this kind of results before because they were using the VR bounds, but using the VIY bound is helping us unlock, let's say, the potential of those alpha-based methods. Okay. Time for an example, just to see, what happens to this theorem when we consider like some sort of, a simple case, I'd say. So I'm going to assume that my relative weights, so those are my W's, theta phi with a bar, are log normal. Anyone knows what log normal means? Yeah, it's written there. I just had like, okay, fine. So basically, if I take the log of my relative weights, this is going to be normal distribution. So I'm introducing S1 up to Sn, which are there, and then I give them standard deviation and a mean. Here, those terms, they are written in such a way that if I take the expectation of my relative weights, which is written there, it's going to be 1. So if you remember, I insisted before the relative weights, I want them to have expectation 1. So a sanity check that you might want to have is like, okay, what happens if I look at their expectation? It is indeed 1. So we're not doing foolish stuff just yet. Okay, so those are my log normal weights. And if I assume this particular form, I can give the expression of the terms that appear in in theorem 1, in like the prediction that I have in theorem 1. And as a matter of fact, this term is going to be minus alpha sigma squared d divided by 2, which kind of might help you visualize what I was telling you before about the fact that it decreases away from 0. I'm talking to people. This is linear, so it's like the perfect example. And the gamma alpha squares are going to be of this form. Okay, so let me, do a bit of like inception and give you an example within the example. And I'm going to be taking my posterior density as a normal distribution with parameter theta, and my variational approximation as another normal with parameter phi. And I'm going to setting up theta and phi so that I am under these conditions. Okay, so if I take theta, which is 0 times the unit vector dimension d, and phi, that is just the unit vector, then I satisfy this log normal distribution of their relative weights with a sigma that is equal to 1. Okay, so we've got some sort of practical example in which we can apply our theorem 1. So how does that work in practice? Well, I'll need to be able to track my variational gap, which I can do using unbiased Monte Carlo estimators. And I need to be able to represent my theorem in a way that makes sense, because so far what I had is like a term that is negligible in front of 1 over n. Okay, we'll just do this by looking at functions of the form of theorem 1 plus a constant, like plus a parameter divided by n. We go simple here. Does it make sense? Yes. All right, so let's look at what happens in this example when we run our simulations. So we've got 3 things. This is alpha equals 0, alpha equals 0.2, alpha equals 0.5, dimension 10, and dimension 100. So I'm going to start with this plot. Do you think that theorem 1, my prediction, is a good prediction of my Monte Carlo approximation, which is in blue? So the violet is my prediction according to theorem 1. Is it a good prediction?
Why is the line so thick, the violet line?
Is the what?
It looks like on the top right plot, the violet line is a lot thicker than the violet line in any other plot.
Yeah. It's true. Yeah, we're going to get to this.
Okay.
So, but first we need to solve like this question sort of I've asked you. Does it look like it's a good approximation to you? Yeah, pretty good approximation. I move to here. We see that this axis is suffering a bit. So is it still a good approximation for low value of n? No. Here, look at this minus 1,400, pretty bad approximation for values of n that are still like 300, right? It's not a good approximation. This is just dimension 10. We go to dimension 100. This is minus 1.75, but here there's like 1 exponent 42, so not good. And even though we had good behavior here with alpha equals 0.5, it's starting to, it's like pretty bad there because it's minus 8, 1 to the power exponent 9. Okay, so what this tells us is that theorem 1 is pretty nice, but does it actually reflect what's going on? So there's something that I kind of put under the carpet when I showed you the example, and which we will now look into to explain this kind of problematic behavior. So basically, if I take this back again, if I now tell you what it is that I was hiding from you, it's this thing. So in my gamma alpha squared, which appears in that term, I've got a dependency in the dimension. And it's not just any dependency in the dimension, it's like exponential in the dimension. So this is a problem that I can sort of alleviate with the choice of alpha. However, the understanding that if I keep increasing my d like crazily, this term's going to blow up. What does it mean on a high level? It means that theorem 1 may not capture what is happening in high dimensions, and that we may never use this n large enough so that we get our asymptotic regime to kick in. Okay, so this is quite a problem with theorem 1. It doesn't mean that theorem 1 is bad. Just say that if you wanted to use it with small values of n in high dimensional settings, this might actually not work. So realizing this, we were like, okay, what about we try to analyze our variational gap as both d and n goes to infinity. Theorem 1 was assuming n goes to infinity, d is fixed. Let's see if we can get some sort of asymptotical result as both d and n goes to infinity. And I'm going to indicate this by now having a dependency in d in my variational gap.
I have some more questions. So in the Gaussian example that you are explaining before, do the relative weights follow the log normal distribution?
Yes.
Okay.
Yes, with a sigma equals 1, when you take when you select specific choices of theta and phi. So I've taken them so that they, as you increase the dimension, they're very far away from one another. Yeah, good. So now we're moving on to part 2, which is let's try to see if we can derive theoretical results when n and d go to infinity in the variational gap. So the key intuition that we had was to actually trace things back to the log normal assumption that we were making on the relative weights. And we're going to say, okay, it might actually be likely that in practice, in high dimensional settings, our relative weights might have a log normal distribution, okay? So we'll get into the detail as to whether or not this is reasonable, but that was the intuition we had when we were working on the paper. And for them, we were like, okay, let's try to understand if we can get a theoretical study in the log normal case. So we will see this a bit in more detail, but this will, we don't just let like d and n go to infinity and we get a result. We need to have actually some sort of relationship between n and d, which is going to be this one. And then the second part is going to be, okay, log normal is nice, but can we get something, can we get another result when we're approximately log normal? Not exactly log normal. We've got like, complicated data. Maybe we're not going to see something very like, nice and log normal. Maybe we're going to be an approximate case. So this is going to be the second case, which I will go into. I'll tell you what I mean by approximate log normal case, should I have the time. But for now, let's go with the log normal case. So here's the main result that we have, which I'm going to refer to as theorem 2. So S1 to Sn are my IID random variables. I'm assuming that my weights might have a log normal distribution of the form we have seen in the example 1. And sigma is positive, of course, as otherwise it's not super interesting. And then we have this kind of asymptotic results. So this is a result that holds for alpha that is between the range I've been interested in so far. And this asymptotic result tells us that if I take the limit when n and d go to infinity, under the condition I was telling you about, log n divided by d goes to 0, then this limit is going to be 0. Okay, so informally, what this says is that this variational gap is going to behave like this term. Okay, so it's going to be minus d sigma squared divided by 2 times 1. So this is going to be my leading term, minus a term here, which is log n divided by d. So under my assumptions, it goes to 0, and those terms, like this is the squared, so it also goes to 0, and this one also goes to 0. Okay, so basically what I want to say is that those terms are all negligible before this, in front of this one. Okay, the leading term is minus d sigma squared divided by 2. So,
Kamélia, one question. You may have mentioned it, and I was sort of dozing off. The weights you choose. Why is it reasonable to assume that they're log normal?
and that's an assumption that we're making, and I'm going to give you an example where it's true, basically.
And does it empirically usually hold? Is there like some?
In some I've got one empirical example where it works, and it's our feeling that kind of the best you can hope in high dimensional settings is that this is going to be a bit log normal, because in that case you can provide the theoretical study. It might not be the case all the time. We've got one example that is real data-ish where it holds. So we think that we should look a bit more into whether or not this holds for several examples, but basically, we're going to show it's not completely far-fetched to look into log normal assumptions. Yes.
About the assumption, why is there the assumption of particular relationship between the mean and the variance?
Because what we want is something that is exponential in D between the mean and the variance, so that this is expectation 1. The expectation of
okay, yes.
Yes. Okay, and the other thing I wanted to say is that my relative ways to have a behavior that is exponential with D, so to relate to really what we saw in the log normal case, like that we have a term that will behave exponentially. Thank you, very, very good point. So this is formally what happens. And if we try to now put this into perspective with theorem 1, here are the two results next to one another. Basically, what you should take away from this is that while increasing n does play a role, it's quite negligible in this analysis in front of this leading term, which is kind of what I was telling you already. Secondly, and this is quite important as well, there's no more alpha in this leading term. In the one I was showing you before, we had minus alpha sigma squared d divided by 2. It's no more the case. This means that the result that we have, which characterize what happens in high dimensions, predicts that there's going to be this leading term for all values of alpha, which is actually quite strong. It doesn't say, oh, we should just always take alpha equals 0, and then, we don't have this term. It says, you can take alpha equals 0, you can take the EYA, you're going to be in trouble as well. And this trouble, if we were to summarize it in 2 words, would be weight collapse. So basically what happens is that you might have n that is not 1, that is bigger than 1, but unfortunately for you, and I mean for me, what happens is that it's not enough unless you get out of this condition, which is log n divided by d does not go to 0. If you are under those assumptions, then you can show that your variational gap behaves like the evidence lower bound minus the log likelihood. So you've got a collapse to the evidence lower bound. Does it make sense for everybody? And it doesn't, at least under our conditions, unless, log n divided by d goes to 0. So this means that if you want to kind of mitigate this effect in the log normal case, you need to take n that is exponential in d, which is a crazy budget that you definitely don't want to use. All right, so that's kind of the sad news about the log normal case. But let's see if it actually, if I go back to my Gaussian examples I was giving you before, if this prediction becomes accurate as I increase the dimension. So I was telling you that I'm log normal with sigma equal 1 in the when I was choosing theta and phi as written there. So that follows from your comment thing. And in that case, I've got 2 competitive sort of interpretations, 2 competitive asymptotic results that I predict. I've got theorem 1, we already saw the curves, and I've got theorem 2. So in order to represent theorem 2, I'm going to do the same as what I was doing here, which is I'm going to just approximate, like just say that this term is like a constant, or like it's like a function that depends on C. Basically what I was doing. Hopefully this makes sense for everybody as to how I represent theorem 2 using simple curves in practice. Does it? Yes? Okay. So, oh yeah, and this is something that tells us like, this is literally the simplest example you can think of, yet to have a weight collapse phenomenon. So we should be very careful when we design our algorithms, because weight collapse might happen even in simple examples. So those curves, you already know them, and I just put them here so that we could breathe a little bit, and see something we had already seen. And now I'm going to talk you through the curves that we've made when we look at theorem 2. So here are the curves, same ideas before, dimension d equals 10, 100, now we're getting a bit crazy, we go 1000. This curves alpha equals 0, alpha equals 0.2, alpha equals 0.5. So what we see is that what we're predicting here with theorem 2 is not accurate in dimension 10. That's not too surprising because we've shown that theorem 1 actually applies. We see here that dimension 10 starting to look like it, but still not super striking, just for very small values of n. And here may be better. So we see that, this alpha can sometimes help in low dimension. However, if I now increase my dimension, I go d equal 100, go alpha equals 0, it's pretty much starting to look like what I'm predicting with my theorem 2. Less true if I change the value of alpha, and especially if I take this alpha equals 0.5. I see that it's reasonable here, but this part, not so much. G equals 1000, regardless of the value of alpha, I'm fitting within the prediction I'm making. So this supports theorem 2 in high dimensional scenarios. Okay, are we good so far, or do you have any questions? Good.
I just want to come back to the log normal assumption of the width. So, it's true that it's just because when you are in the high dimension, then each dimension you add, it's kind of a central limit theorem that makes the log normal.
Maybe I think we haven't formalized anything. It's like, I mean, we would be curious, but that was our intuition. It was like, it might become log normal. That might be the thing, but we haven't proved like anything formal about it. So I wouldn't know. But interesting, direction of research, like trying to understand whether how reasonable it is and how much we can observe it. Thank you for the very good point.
That's something that I think, if I'm not wrong, that for important something, you have the ways asymptotically behave like a log normal.
Okay.
So maybe even for SMC, I'm not entirely sure about.
Yeah, that's why I was asking the question, because it does the same case. You have eight dimensions. You have the kind of the central limit theorem effect that you transform to the log scale, and then you have.
So there is at least one case in which the ways do behave like log normal.
You feel like writing a paper about it. Yep. So yeah, in the chat they were saying that they were trying to validate the assumption that I'm making on the log normal weights and the weight being log normal. So I'm very grateful for that. And a few examples based on SMC and important of them. Right? Did I get that correct? So basically, they're helping me do my talk, and thank you very much to you for this. Okay, so that was the log normal case, but we kind of understand that this might not particularly reflect what happens in the reality, that we might be actually log normal case. So we need to look into what happens in the approximate log normal case. So I'm going to define what we consider as approximate log normal. So I need a bit of assumptions. Maybe those assumptions could be different, but basically we wanted a working framework in which we could say something. So I'm going to introduce SI, which, they used to be log normal, but now I'm going to have like central limit theorem as well, in which I have 1 sigma square root of D and a sum of a D of those random variables, which are indexed by I and J, and they go from 1 to D. And I'm going to make assumptions so that this becomes log normal. This becomes normal, sorry, as I increase the dimension. So I'm going to assume that this has like expectation 0 and variance sigma squared, okay, which is infinite. And this is another condition that we have, but I don't want to, if you want to understand this condition, you need to look into the proofs, which are pretty difficult. I mean, the log normal case was not too hard to derive, but the approximate log normal case is definitely the piece that was the hardest in terms of theory. So I'm not getting too much into this detail. And what I'm going to say now is that approximate log normal weights is going to be kind of similar to what I had seen before. So I had my SI, which I expect to be normal 0, 1. I'm going to give them standard deviation term, and I'm going to have a mean term, which is such that if I look at the expectation of my relative weights, this is going to be 1. So you can do the mental check if you want. Basically, if I just take this to the exponential, and I expectation, this is built in such a way that this is the expectation is going to be 1. Do you guys see it, or?
With the second assumption, that's basically exponential tails, or up one thing. So there exists k greater than 0, blah blah blah.
It's not even. It's like, let me this.
Probably.
Well, that's the same. You want to wipe.
So basically, it's like. This is the moment where I shouldn't mess this up, but I feel like I'm going to lose it. So,
Don't worry, everything's recorded anyway.
so I guess it's something like this, right? I'm writing this under your control, so right. So I take the expectation
No, sorry, I mean, so the number 2 under assumption 1,
Yeah.
there exists k greater than 0.
Yeah, sorry, I
This
didn't.
is basically saying that the xi's have at most exponential tails.
So if you want me to get into a bit of the details, basically what we're going to work is that then we're going to look at like the distribution of the weights, and we want to have a result so that we can say, oh, it looks like normal distribution. That's what you were saying, I guess.
Yeah, kind of.
Yeah. So this is why, we need a bit of control to be able to. This is kind of what the proof is about. We're going to say, oh, the distributions are actually looking normal, and this assumption is needed in order to have this kind of results.
So is it basically a sub-Gaussian assumption?
I think it's a bit weak.
Sub-exponential or something, but it's something like that.
We call it something called a leaderable CLT, something like that.
This is like a Bernstein condition, right?
Yeah, something like that.
So I'm bad at names. Okay, yeah. But definitely, like, you can look into the paper, remember writing. It flew out my brain. Okay, so if you just introduce this condition A, if you introduce A as this quantity, you can rewrite the approximate log normal weight under this slightly more compact notation, which is minus dA minus sigma square root of dSi. And you can, I'm just going to, you can check that size. Should you want to, should you, I'm just going to say that it's true. Forward. So here's the main results, which I'm going to refer to as theorem 3 in the case from A1. And that's my relative weights by this condition, which is the one I was giving you before. And under my assumptions, if I will have that A is non-negative, and that for all alpha, now I'm worried because I'm like non-negative, non-positive. I'm going to say, and I'm going to have this asymptotical results, which will hold for all alpha that is between the range I've been interested in so far. Basically, takeaway message is that I'll be in a pretty much similar situation as to what I was seeing in the log normal case, except one thing, which is this thing here. So basically, when you are approximate log normal, the condition that we had before, which is n must be exponential in D, is replaced by the condition, if I want to get out of this weight collapse phenomenon, n should be exponential in D 1/3. So it's slightly weaker, still quite stringent. But it tells you that depending on the distribution of your relative weights, you might actually move from this exponential in D to something less stronger. And it gives us the idea that maybe in some cases we can find weaker conditions on the behavior of n. Still, in that case, pretty restrictive, again, as a function of the dimension. This is just a side remark. There's no dependency here left in alpha. We had one before. This is just because we're working under this stronger assumption. And basically, if we now want to represent theorem 3, it will not depend on alpha. So the curves that you're going to see later, I'm going to group all the alphas together. So I just didn't want you to be too shocked and be like, what's going on? Where are my orange curves? It's just because now they're going to be green, by the way. It's just because now there's no alpha anymore. So I'm just going to group them. Okay.
Can I just check my intuition? So with this, compared to the log normal case, you can accommodate more general things. That's correct?
Yes.
But then you also get a weaker condition on the end that you need to stabilize.
Yes.
But so does it then completely supersede the previous theorem?
So basically, in a sense, what the previous theorem gives you, I'm just going to get closer to that, is that you have a better idea of, how much you can push your n, right? Like before things, start to get better. So it's a better result in a way, because it tells you, oh, things fail until you are more than exponential in the dimension. This result, what it tells you is that, oh, it's exponential in D 1/3. It might actually be more than that. So it's a bit of a tight line. What it says is that log normal might be the worst case yet. And if you move slightly away from this, you might actually not have to be exponential in D. Do you see? It's like
sort of, but does this theorem also applies to the log normal case?
Yeah. It's that in that case, it's less strong. Do you see? Because it's
okay. It's sort of.
Do you see? Yeah.
Okay.
Because it says like this one say, oh, maybe if you go over exponential d1/3, your life gets better. The previous one says, no, 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 no. If you want lives to get better, in the log normal case, you need to be exponential in d. Does it make sense? It's a bit like
Yeah, I think so.
fantastic. Could be a bit confusing. Okay. All right, so I'm going to give you a slightly more involved example. And what I mean by involved is that it appeared in the literature. So incredible that we can make our assumptions fit in that framework. And it was introduced in a paper by Renforth et al. In ICML 2018. And it's a linear Gaussian example. So, okay, not the fancier stuff around, but, you know, still an improvement from just my Gaussian example I had before. So in this example, I'm going to specify my prior, I'm going to specify this thing, and basically my parameter is going to be the one in the prior, and my variational approximation is going to be of this form. So I'm going to play with like a matrix and a vector here, which I'm going to be trying to tune. In fact, I'm just going to be trying to tune in RD times RD. So basically, this is just the setup. We don't really need to think too much about it. What is important is that if I use this kind of formulations, if I choose my model to be like this and my variational approximation to be like that, then I can say that my relative weights will be approximately log normal, meaning that I can write them under this form where the SI is the one from before, and I can identify sigma squared and A. And they depend on this lambda. So this is like, you don't really need to get too much understanding of that. I think what is important is my assumption A1 will hold if I take my theta and my phi to be the optimal one. So I have my model and I have like my variational approximation. I take the best parameter for my model, the best theta, the best parameter for my phi, so phi star and theta star, and I'm still under A1. Okay, so this sends quite a strong message. It says even at optimality, you can be in a situation where our results of theorem 3 might apply. Why is that? Is because in fact, at optimality, you still have a mismatch between your pursued density and your variational approximation. Does it make sense? Like the variational family is not big enough to capture the complexity in the posterior density, meaning that even though I'm at optimality with theta and phi, I am under the approximate log normal condition, and I satisfy A1, and theorem 3 might apply. Does it make sense? It's quite important. So yeah. So I have in that case those two competitive or how to say it, remembered it. There's two competitive results. In this example, everything is kind of tractable again. So, you know, my VR bound minus my log likelihood is still tractable, and the gamma alpha squared is still tractable as well. It looks very exponential in D. And I have theorem 3, which is of this form. And I now want to show you what goes on empirically for this example. Oh yeah, this is also to say, wow, here we were at optimality and things look like they can go wrong. So this means it's important to be very careful with the choice of your variational family, because the result that we have says that all those bounds, they basically might encounter several problems if your variational family is not good enough. So it's kind of moving into saying that in variational inference, we need to put a lot of effort in also improving our variational approximations. Otherwise, all the bounds we have might just not perform to the best of what they can. Okay, experiments, dimension D equals 20, 100, 1000, alpha 0, 0.2, 0.5. So dimension 20, not bad. Okay, so how can we explain this? We can explain this by the fact that we're now approximate log normal. Okay, so like you were mentioning, it's not like exponential in D, but it's like D1/3. So actually, even if we take alpha equals 0, dimension equals 20, this is not too bad of an approximation. Dimension D equals 100, still pretty good. We're starting to see that there might be a mismatch here. Dimension D equals 1000. We run into trouble, right? For those values up till, let's say, 100 or 200, this is not actually a good approximation. Theorem 1 fails as we increase the dimension, which corroborates what I was saying with so far by my approximate log normal assumption. And this, you find it regardless of the value of alpha that you consider. All good? Moving on to our green curves. So in that case, so yeah, I didn't say, so we're at optimality here, right? So theta is the optimal one, phi is the optimal one. So here are the curves. So d equals 20, doesn't look super convincing. D equals 100, prediction by theorem 3, not so convincing, starting to appear here. Dimension d equal 100, the prediction between 0 and 100 starts to be more believable. So this was when we considered our parameters to be optimal, and we also wondered what if our parameters are not optimal, because it could be in a situation, right? It's not every day that you are at the good parameters. So what if we perturb a little bit those parameters? So this is if we perturb slightly. So I just put like a Gaussian normal noise sort of with this variation, so not much change, and then I'm going to perturb them a lot. And here are the curves that we get. So basically, as you get further away from optimality, right, this behavior that we predicted gets worse, which makes sense, right? If at optimality, we're supposed to be approximate log normal, if I get further away from the optimal, then I'm really expecting that this theorem 3 will kick in. Make sense? Okay, 43. At this stage, so this is another one where we breathe. Here's what we've looked into. We looked at the variational gap, and we have given 2 studies that I think are complementary. On the one side, we've got a study when n goes to infinity and d is fixed. And on the other side, we've got a study where both n and d go to infinity with some sort of link between n and d, right? So there's first one, which is the log normal case. Then there's the second one, which is the approximate log normal case. The main idea and the main reason why we say that those analyses are complementary is because what we think is that the first one is in fact tailored for low to medium dimension settings. And we think that the second analysis reflects more what might happen in high dimensional settings. Okay, so it doesn't, basically what we're saying is that, oh no, theorem is so bad. No, it's not bad. It's just that it applies in some specific cases. And you need actually to be careful about this gamma alpha squared. If it goes up, it's going to mess up a little bit the asymptotical regime predicted by theorem 1. Okay. So question, can we now try to apply what we've learned to a scenario where we don't know everything, basically what we usually do in variational inference? Make sense? Any questions?
Oh, just with regard to this question, it doesn't seem obvious to me because you have currently you have a family with 2 parameters, and I do not see an obvious way to transfer that to the where posterior density is not up to the constant.
Watch me. Yeah, but that's a good point. I think what you're saying is that it's difficult to know how we move from the case where we knew all the quantities to the case where we know things up to a constant. So it's actually a very valid question. And it's the topic of my next slide, which is from theory to practice. So the first thing that we need to do is to check that, the quantity we're interested in this time is going to be the VI way bound. It's not going to be the variation gap anymore because I don't know my marginal log likelihood. So I'm going to work with the VR EY bound, which makes sense. This was my quantity of interest. And I'm going to be like, this is not difficult because I know an unbiased estimator of this VR EY bound. So that's the first point. This is not. The second point is that I had my 2 theorems, theorem 1 and theorem 3. And if I look at them, they involve quantities that I don't really know. So they involve the marginal likelihood mainly, and they involve sigma. So there's a bit of uncertainty going on around here. So for the first one, I can make my life simpler. So this is again VR instead of L, and I can remove this log likelihood, marginal log likelihood term, because I had VR EY bound minus log likelihood equals VR bound minus log likelihood plus this term. So I just drop the marginal log likelihood from both sides, and I end up with this. okay? And this I can estimate. So I can, it's going to be biased, but I'm just going to estimate it by taking a large number of samples to see whether or not this is a good interpretation. The second one is this one. And what I'm going to say basically is that I can rewrite this thing as this thing that is written here. So basically what we do is just that we remove the marginal log likelihood once again. Then we've got the evidence lower bound, which is something that we can estimate. And the other quantity that we don't know is the standard deviation of that appears in the relative weights. So what we're going to do is that, okay, things are starting to look approximately log normal. I'm just going to estimate it, right? I'm just going to look at the distribution I get, and I'm going to get an estimator of this one. So in practice, all those quantities that appear, you can kind of approximate them, which hopefully answers your question, Dan. Yeah, does it?
Sorry, I missed this. Can you say again in theorem 1 why we're dropping the log likelihood?
If you have the VREY bound, that like this term is VREY bound minus log likelihood, marginal log likelihood.
Oh yeah.
So you don't need it actually in the case where you don't know the normalizing constant. Yeah. So this is the reason why this one is a bit trickier, but basically this DA, do you remember when I was telling you, oh, there's a weight collapse, it's like elbow minus marginal log likelihood, that's what we're using. And this is why the DA disappears. There's no A anymore, which is great because it's one less thing to estimate. And it also tells us, oh, this it might be even easier to visualize what I was telling you about this weight collapse, because this means that the EYA bound, the why is it called EYA? Oh dear, of course. No, okay. I was worried for a second. This is the VREY bound, behaves like the evidence lower bound plus like this term, sort of, okay, which is negligible under our assumptions before the evidence lower bound. So really like my VREY bound is some sort of elbow plus some terms, okay, which are negligible. All right. I think we'll have time to look at an application, real world application. You don't know how privileged you are because I don't have that many of them. So I'm going to look at variational autoencoders. Again, I don't want to start on the talk, which is going to be in the afternoon. So like written here, more details about this framework are going to be given in the afternoon lecture. Here, we're only interested in two things. The first thing is the behavior of the relative weights. And the second thing is the behavior of the VREY bound, okay? So behavior of the relative weights, we're looking at like one observation, and we've got like this follows from other observation, but for readability, here's one observation. And we're going to be looking at the relative weights to check whether they are log normal in several dimensions. So dimension 5, 10, 550, 100, 1000, 5000. This is a QQ plot, and this tells us that actually it's something that we believe that we might have some sort of log normality happening, or at least like an approximate one, right? Because it's like real world, so we can't be like, oh, it's log normal. It's probably something that is approximate. Does it kind of satisfy? It's chatting with Saf. I was like, this is the plot that you wanted to see.
I was making fun of the fact that MNIST is the real world.
You don't know where I'm coming from. But I'm very happy if you can show it applies to other super nice data sets, definitely.
To be fair, I think that's a very impressive fit.
Okay, yeah, no, but I do think that, I mean, you know, we just wanted one example, and I think the key idea is just to see, oh, it's actually something we can believe that happens. Okay, so we have a bit of time left, which is great. And I'm back with my plots for theorem 1 with my alpha as 0, 0.2, 0.5, and I'm looking at dimension 50, 100, 1000. So this is the conclusion that we usually have. So it's actually believable dimension 50 that my theorem 1 predicts well the behavior of the VREY bound. Okay, so this gives us the idea that, you know, actually we are low to medium dimensional settings when using theorem 1. If I increase to dimension d equals 100, alpha equals 0.5, still not doing too bad. 0.2, we're seeing some sort of mismatch. 0, we're starting to see an apparent mismatch between theorem 1 and what I predict in violet here. Pushing this dimension 1000, this mismatch becomes much more obvious, including for values of alpha that is 0.5. So we're still going on with, everything I've said so far. The plots should feel very familiar. And let's try to look at what happens now with theorem 3. So dimension 5 does not apply too much. We're in too low dimension. Dimensions 10, again, 50, 100, we're starting to see something that resembles what we predict. 1000, we're starting to see this for higher values. And if we go 5000, like it's actually very believable that what we're predicting with our theorem 3 might reflect what is happening in practice. All right, another pose. At this stage, we've seen 2 complementary analyses of the VREY bound, which we have verified on a very real-world scenario. The first theorem is tailored for low to medium dimension setting. The second one we think applies for high dimensional settings. Any question that are not pertaining to real-world scenarios? Or is everything clear? Okay, so again, if you don't have questions, I have questions. Can we say something now about the gradient of the VREY bounds? Because we said much stuff about the bound in itself, but it's also interesting to try to get an understanding of the gradient, although honestly, this is much more difficult to do. With the VR bound, we could actually do things. With the VREY bound, there's reparametrization, so this makes the analysis harder. So I'm probably going to skim a little bit through this because I don't have that much time left. Basically, this is not like this time we're not breathing because we didn't go through all the slides. But basically, what we have shown is that if we look into the signal to noise ratio, anyone familiar with the signal to noise ratio? Maybe no. Okay. So basically, if we look at the estimated gradients of the VREY bound, and we look at those reparametrized estimated gradients, we can wonder about whether or not there's a good signal to noise ratio. So if we look at them in expectation and we divide sort of by the variance, by the noise, do we still get a good behavior as a function of n? And basically, the result that we get, so we've got, 2 parameters, we've got theta and phi. And we're going to say that we said phi is in RL. And I'm going to say, okay, theta is also in R, let's say to L prime. Then we can look into this signal to noise ratio and have some sort of an idea of the behavior of the reparametrized estimated gradient of this VREY bound. So what we get, and this is like, we're just going to go high level, is that if you look at the signal to noise ratio, when you work with the theta parameter, this increases as you increase n. So this gives you the idea that increasing n is actually good for your algorithm. If you look at the signal to noise ratio with respect to phi, the story is a bit different. For in particular, if you take alpha equals 0, you have that the behavior is like square roots of 1 over n. So this means that if I increase n, my signal to noise ratio is actually going to decrease. So this is a problem that has been identified in this paper by Renforth and co-authors in ICML 2018, which you might have already seen. It's called like tighter variational bounds are not necessarily better, and basically they show that there's a problem in the gradient when alpha equals 0. The key message is that by playing around with the value of alpha, we can actually recover a behavior which is a square root of n for the signal to noise ratio. So this is when this alpha is between 0 and 1, which tells us that it's actually important to move away from the EYA. And of course, it's not like a stark contrast between the two and can pretty much get the idea that in practice, if you take alpha equals 0 and 0.0001, you might have some signal to noise ratio problems. But basically, this paves the way towards using alpha that is non-zero. It actually promotes the use of such values of alpha, especially because there are issues that have been identified for the EYA. One last thing, but this is really like a bit of a connoisseur. Reparameterized estimator are one thing, and since then, because people realized that we had this big problem, they developed a different reparameterized gradient estimator, which is called doubly reparameterized, to alleviate the problems encountered here. As it turns out, because our VI bound is the extension of the EY bound, we can also extend this doubly reparameterized gradient estimator to the VI bound. This is another way to say, okay, we've got this more general bound, and it's highly likely that many things that will improve on the EYA will improve on the VI bound. So next time you work on the EYA, take some time to consider the VI bound, because you might get even better performances. Okay, so almost my time is almost up. So
Can I just ask a question regarding the gradient? What is the advantage of using it with the VR bound? Because basically the advantage is that you can correct the signal to noise ratio.
Yes.
Basically, what is
it gets even better. That's the curves I'm going to show you. So basically, this is like for the linear Gaussian example, the one considered in Rainforth and co-authors, and dimension 20 in the reparameterized case. So we really see the problem of the case alpha equals 0. This is this curve, like alpha equals 0, and it goes up to alpha equals 0.9. So this decreases, like the signal to noise ratio. As you increase n, it decreases. So it's like the message that was being sent. And as you increase the dimension, you see that it matters to play with the alpha, because the signal to noise ratio actually, improves as alpha increases. And if you work with a doubly reparameterized one, basically what you need to observe is that the order of magnitude here is going to be higher in this curve. So doubly reparameterizing is not just improving on the EYA, but in our experiments, it's also improving on the VIA. So I guess that's kind of another way to just shows that playing with alpha does not seem to be detrimental, even though you apply techniques that were tailored for EYA bound. Okay, this is just if you increase the perturbation, I'm going to skip this. This is theta. This was kind of known already, so it's just that there's no such decrease, even though you have alpha equal to 0. And we've got similar sort of results for MNIST, so I'm not going to go over that. I just want to conclude over this plot, because you could leave that talk thinking, okay, should I use this VR EY bound? There seems to be some advantages or not. What I've gone to say is that in some problems that could be low to medium dimensions, there are some improvements that you can get. And in this one, it's like the MNIST data sets. And basically, we compare the reparameterized and the doubly reparameterized approach. And basically, you can see that there's reasonable, it's reasonable to think that playing with alpha might actually improve. So we took n equal 100 here, and we see that the optimum is actually not the EY bound. Okay, so I think there's more work to do to make sure that those methods actually scale better. And the important takeaway message is that the problem is not the fact that we're using alpha, and it might pertain a bit more to how you create your variational approximation, which brings me to my conclusion. I'm almost on time. So if you want to know more, please do check the paper. And here's the overall recap. We formalized this new VI bound, which used to be just seen as an expectation. We've got nice theoretical guarantees. We extend the EY bound. We've got 2 complementary analyses, shedding light on conditions that might lead to the success or failure of those VR EY bound methodologies, and that apply to the EY bound. So this is important if you come from the EY community. So after you're like, wow, this actually applies to what I'm interested in as well. We looked very briefly into the gradients of the VI way bound, and we saw that there might be desirable properties in terms of, signal to noise ratio, doubly reparameterized approaches, and we've empirically verified our theoretical results, although further empirical work could definitely be done. Some perspectives, some open questions, in my opinion. Does that weight collapse behavior apply beyond the cases I highlighted here, and under what conditions on L and D? How does the weight collapse affect the gradient descent procedure? That would be the step forward. And can we use the fact that the VI way bound extends the E-way bound further? That's what I was telling you. Maybe just using the methodology built for the EY bound might actually transfer to the VI way to get better gradient estimators, or just to work with larger variational family Qs. So now I'm just have to thank you very much for listening to me for so long. And here are just some references that you can definitely check out later, and I'll take any questions that you might have.
If there's any quick questions, I'd say let's go ahead, but otherwise, are you around for lunch?
Yes.
Great. Okay, maybe let's keep them for lunch and maybe take a quick break and then start again with the second part. Is that okay? Because I need a break, guys.
You want to ask questions? And from the chat, yeah, if you want to ask a question, probably hang around here. Otherwise, just shoot me an email. Right.
Yeah.
Is
it okay?
For the call center.
Yeah.
Where?
You operate this. Yeah.
Oh, I sent.
No, I mean, did you operate all the elements out of one? Okay, thanks. Ah, okay, so.